Fellow Pokeprofs, have you ever wondered how snowflakes form from their unique shapes? Most of the time they are like hexagons in that they have six-fold symmetry. But did you know they can be just about any shape? Why do snowflakes have these shapes? And why do they always look different? Today we're going to explore the science behind the fascinating form of precipitation called snow. Snowflakes are beautiful and symmetrical, but the process of how they form is not completely understood. Scientists can determine the structure of crystals using X-ray scattering, but predicting how they will grow under different conditions is difficult. Snowflakes can have different shapes due to the speed at which different faces grow. Scientists are faced with the challenge of understanding how water freezes to produce different crystal structures. Studying the crystal growth of snow should help us understand the formation of patterns and structures in nature. It can also help us predict the weather more accurately. It is amusing that we still know very little about snow. Here are 3 questions that seem basic, but are still unsolved. How do crystals grow? How can snowflakes have different shapes even though they all start as hexagonal prisms? How can studying snowfall and snowflakes help us better understand nature? Snow is not just pretty. It's also very important for creating lightning and catalyzing other reactions in the atmosphere, such as the natural decomposition of the ozone layer. Snow is a form of ice. It is solid water. It is also a dielectric, which is to say it does not conduct electricity well. This means that it has a well-defined surface and can carry a static charge. The structure and behavior of snow crystals can change the nature of the meteorological phenomena that is observed. From a meteorological perspective, a snowflake is a spherical clump of snow crystals. As such, we could better understand the weather and even influence it by understanding snow better. Therefore, let us discuss these questions. High up in the atmosphere, water vapor has the chance to turn directly into a form of ice in a process known as deposition. This is basically condensation and solidification all in one step. If it is very cold and very dry, snow crystals look like simple hexagonal prisms. If it is more humid, they look increasingly more and more complex, first forming columns or needles, and then the signature hexagonal form. For a snow crystal, or indeed any crystal, to form, there needs to be something for the crystal to grow out of. Effectively, the crystal is like a flower. They both grow from seeds. For crystals, however, a seed could be just about anything, as long as it is small enough. A speck of dust, a grain of pollen, a crystal of silver iodide, which people sometimes use to encourage the formation of rain or snow in areas experiencing drought. So cryogonal would be born from dust, not in a biblical way, but in a literal way. In the Pokédex, it says that people and Pokémon who die on snowy mountains are reborn into these Pokémon. Are we all just dust then? We are. We are stardust. Why do snow crystals and snowflakes even form? Does nature somehow prefer beauty? It isn't even about beauty. It's about physics. There are 4 stages to the formation of a snowflake: nucleation, facet growth, dendrite formation, and fractal growth. Nucleation is the birth of a crystal. A seed or nucleus, such as a dust particle floating in the air, is like a magnet attracting iron, with the water molecules being like iron filings. It is also possible for the ice particles to just come together without the aid of a dust particle or other seed, but this is exceedingly rare. Nucleation is like a chemical reaction. When dust interacts with water, again, just like a magnet, there are intermolecular forces between them. Although these forces are much weaker than chemical bonds. This reduces the total free energy of the system, which is just a fancy way of saying that this is a more stable configuration. Now the ice crystal begins to grow by adsorbing more water molecules. That's adsorption with a D. Adsorption is just like absorption, but instead of the molecules being fully taken in by the crystal, they are only sticking to the surface. The crystal is hexagonal at this point. During this stage, the ice crystal naturally develops faces, technically facets, which are determined by the orientation of the water molecules within the crystal lattice. Notice how the corners of a hexagon stick out a little more than the faces. These corners are going to collect more water molecules simply because they are closer to the surrounding air than the faces. At the same time, water molecules are attracted to the places where the faces and corners meet because adsorption happens more readily in rougher areas, i.e., it reduces the free energy more. The whole crystal grows as a result, at the staggering rate of millimeters per hour. You have likely noticed that the 6 corners will give rise to the 6 arms that we tend to see on ski sweaters, Google Images, and, of course, on Cryogonal. These arms are called dendrites, and they grow at a faster rate than the smoother facets because of an instability related to the diffusion of water molecules. This instability, called the Mullen-Sakirka instability, explains why dendrites form, why they can be so mesmerizing, and why no 2 snowflakes tend to be alike. It is also quite fun to see 12 dendrites on snowflakes due to a crystallographic phenomenon called twinning, but that's beyond the scope of this video. All this time, the snowflake has been coated with a layer of liquid water that attracts more water by hydrogen bonding. Depending on the concentration of water in the air and the temperature, the structure of the dendrites will change. Each dendrite experiences nearly identical changes because they are very close together and travel along the same path. However, ice is, unusually, very sensitive to atmospheric conditions. This sensitivity has been well documented in a graph called a morphology diagram, which we will see very soon. As a snowflake dances around in the wind, it gets heavier as it continues to attract more water molecules from the vapor phase. The air that surrounds us may seem to be at a constant temperature. This is why we can talk about the weather without too much hassle. And it is for all intents and purposes. However, to a microscopic ice crystal, this is far from the case. Minute temperature and humidity differences can give rise to staggering changes in the diffusion-limited growth of the dendrites. Again, thanks to the Mullen-Sakirka instability. The bigger the crystal becomes, the more sensitive it becomes to these differences. This sensitivity is so incredible that even the dendrites on a single snow crystal have subtle differences. Truly, the probability that any 2 snow crystals are the same may be compared to the probability that any two mature complex organisms are exactly identical. Ukihiro Nakaya, a physicist from the University of Hokkaido, Japan, was one of the first scientists to study snowflakes in the lab. He observed the growth of snowflakes under controlled conditions, which helped him develop a diagram that displays crystal shapes based on temperature and humidity. The diagram shows that snowflakes become more complex as humidity increases, and that their overall shape changes from plate-like to columnar and back again as temperature is lowered. However, this behavior is still not fully understood. The diagram represents only a two-dimensional slice of a much more complex morphology space that could include other factors such as time and pressure. Snowflakes grow differently depending on their path through the atmosphere, encountering varying temperatures and humidities that result in each crystal developing a unique structure. Why is humidity important? It is because of a phenomenon called supersaturation. Supersaturation is a condition in which a solution contains more of a dissolved substance than could theoretically be dissolved under normal circumstances. In this case, it is when the humidity of the air is greater than 100%. In the context of snowflake formation, supersaturation occurs when the air is cooled to a temperature below its dew point, causing water vapor to condense into liquid droplets or ice crystals. The dew point is the temperature at which air must be cooled at constant pressure for water vapor to condense into liquid water. In other words, it is the temperature at which the air becomes saturated with water vapor, and any further decrease in temperature will result in condensation. At atmospheric pressure, this is at around -2 degrees Celsius. As the air continues to cool, these droplets or crystals can grow in size through a process known as deposition, where water molecules directly freeze onto the surface of the existing droplets or crystals. If the air is sufficiently supersaturated and the temperature is low enough, the crystals can continue to grow and form complex snowflakes. The relationship between supersaturation and snowflake formation is complex and not fully understood, as it depends on many factors including temperature, humidity, and pressure. However, it is generally believed that higher levels of supersaturation lead to more rapid crystal growth and the formation of more complex snowflake shapes. Even though every cryogonal in the games and anime look alike, typically no two snowflakes are exactly the same. This is because of the complex and variable process of snowflake formation. Snowflakes form in unique atmospheric conditions and are influenced by factors such as temperature, humidity, and air composition. As a result, each snowflake grows in a slightly different way, leading to variations in their shape, size, and crystal structure. Even tiny differences in these factors can lead to large differences in the final snowflake shape, which is why it is impossibly difficult to find two snowflakes that are exactly alike. This is more of a conjecture, waiting to be scientifically proven or disproven than a fact though. Also, Cryogonal is ginormous. At just over a meter in diameter, this makes it almost 3 times as large as the largest snowflake ever observed. It has been shown that applying an electrical voltage to a growing snowflake can suddenly cause it to grow very quickly. So maybe the growth of Cryogonal is stimulated in some way? Nakaya first envisioned his morphology diagram some 70 years ago. But cellular automata have been used to simulate the behavior of crystals growing in 2 dimensions for just a few decades. By varying 2 parameters to simulate changing temperature and supersaturation, these computer simulations can depict many of the recognized shapes of snow crystals. With each shape, having its own electrifying names such as sectored plates, stellar dendrites, bullet rosette, split star, and Suzumi crystal. The formation of snow crystals is a complex and fascinating process that involves the organization of water molecules into a crystalline lattice. The study of snow crystal growth provides valuable insights into the physics of crystal growth, which is important in material science. The growth of snow crystals is influenced by various factors such as temperature, pressure, and chemical impurities, which can affect crystal morphology. Understanding the nanoscale dynamics of solidification and pattern formation in snow crystals can also lead to a better understanding of fundamental aspects of material science. In addition, the study of snow crystals is essential to meteorology, as it can provide valuable information about weather patterns and climate change. How did you find that? The study of how snow crystals grow involves understanding physical processes at different scales and may lead to new discoveries in various fields. Let me know in the comments below what you learned and if there's a topic you'd like me to talk about next. I release a video about every month. If you appreciate the effort I put into making this video, please like and subscribe. PokeProfs, continue evolving.